So, welcome back, and as ever, I do hope you and your family are keeping well. So, what I want to look at in this lesson is power, okay? What we mean by power, and then we'll look at how we can actually calculate some powers, okay? Well, it's a word in the English language. I mean, we all say something's powerful, but in physics, it means something very specific. It means, and I'll explain this, the rate at which energy is transferred. Okay. Now, let's pull that a little bit apart. So the rate, okay, how rapidly, okay, and a good way to measure rate is in time, okay, obviously, and we do it in physics in seconds. I think I'll write that in full seconds. So it's best to look at how rapidly we do something in seconds and how rapidly we transfer energy. If you remember, energy is measured in joules, okay, named after Mr. Joule. So power, something that's powerful, transfers energy very quickly, okay. Another way of looking at this, and I'll change colour just to make it look different, but it means the same thing, is it's the rate of doing work. Okay. Now, that seems very different, but how quickly you do work, you do something, you transfer energy. So it basically says the same thing. Okay. So if you think about it, we're going to measure power in joules per second. Okay. A much better way of writing that at GCSE, of course, is joules per second. I don't think I need to say this to my students, but it's really important. Please don't put a P in there. Okay. I have seen like JPS. It's not correct at all. Okay, joules per second. Okay. Now, sometimes we don't want to keep writing that, so that is the same as, exactly the same as a watt. So we could write, instead of joules per second, capital W. Okay, it's quite an interesting story. James Watt, the guy who was an absolute genius building steam engines, about 1776, with his Watt engine, was capable of doing work, transferring energy more quickly. So it was a higher power. Okay, and then over 100 years later, Wilhelm Siemens in Germany, and he was sort of in the UK a bit later on, about 1882, was on a committee, and they wanted to find a name for the unit that we have for power. And he thought back, and I think it was very generous of him as a scientist who'd come from Germany, to come up with the suggestion that the rate of doing work or power should be measured in watts. After James Watt and his steam engines, and of course I don't think he ever got to know that in his lifetime. It happened afterwards, but what a nice thing to do. Okay, so now let's look at power a little bit more mathematically. And I'm going to do that with a little challenge. I'm going to compare a crane lifting a weight and a human lifting a weight. Okay? What I want you to think about here is, when you see a massive crane on a building site, it's very tempting to say, when it's not running, it's sitting there in the evening doing nothing, look at that, it's an incredibly powerful crane, isn't it? And you made a mistake, because power is how rapidly you're transferring energy per second, and a crane that's parked up doing nothing has a power of 0. Okay? Whereas if you're running around very quickly, you're transferring energy rapidly, so you've got quite a high power. Okay, I usually start this off in class in a very simple way with demonstrating a dim and a bright light bulb. And I switch them both off and I say, okay, that's the really strong bright bulb when it's on, that's the dim one when it's on, switch them off. Which is the high powered bulb then? And you've got to be a bit careful because if they're off, the current power of them at that time is zero. They're both zero. Okay, but if I turn them on and turn them up to full brightness, clearly the really bright one, like the lamp I'm using today for the projector, that's the high-powered lamp. It's transferring a lot of energy per second. So let's have a look at a crane to see if it's going to be more powerful than a human being. So we've put the same masses on the crane, so we're going to lift the same amount, okay? And we'll make this 60 kilograms. 60 kilograms. So that's about the mass, how heavy, I suppose, a human is. Okay, so it's fair to say that a person can lift that much. Just the diagram here, if you're not familiar with this, we've just slung a rope over a pulley or a branch of a tree or something. So we pull down, yep, and the mass will go up. So we've got the same masses, and to make it a fair test, what we're going to do is we're going to lift them through the same height. So let's lift by 20 meters. So we're all there in absolutely the correct units. Okay. Now here's the clever bit. What I want to do is work out which is the more powerful lift. Now, if you remember, we need to know how much energy is transferred in an amount of time per second. So our crane is going to take 10 minutes to do this. Okay, to lift up the mass. Okay, whereas our human's going to yank on the rope and do it really quickly. Well, really quickly. Let's make them do it in half a minute. Okay. So that's quicker than the crane, okay? And again, to make it a fair test, okay, make sure you realise we've got the same mass lifted by the same distance. Now, should feel a little bit uncomfortable at this stage because minutes, we don't work in minutes. So let's do this properly, okay? 10 minutes and there's 60 seconds in a minute. So that's 600 seconds, okay? And half a minute, 30 seconds. So now we've got everything in the right units, okay? So we need to work out the power. How much energy is transferred per second? Okay, so I'm going to write it here. The power is the energy transferred per second. Okay, power is the work done per second. Okay, well, to work out the power of the crane and the power of the human, we need to work out how much energy they transfer and divide it by how long they took. So this is a little bit complicated, but hopefully you remember something about the energy transfer here. Okay, what we're doing is we're having a gain of gravitational potential energy. Okay, we'll call that energy. Okay, and I'll put a little P down there to remind us that the energy we're dealing with here is raising the block up. It's gravitational potential energy. Now you might remember that the formula for gravitational potential energy, okay, is mgh. Okay, so the mass that we lift, okay, the strength of gravity where you are, the gravitational field strength, and the height that you lift it through vertically. Okay. Now, G is 9.8 newtons per kilogram, but let's make it easy today. Let's just call it 10. Okay. So, how much energy we transfer when we lift these things, okay, the energy gained will be equal to the mass that we lift, 60 kilograms, times by the gravitational field strength, 9.8 in the exam, but let's round it up to 10 to make the numbers easy, okay, times by the vertical height. You've got to lift upwards, okay, lift away from the earth, and we were lifting by 20 meters. So the energy that's gained here, 60 times 10 times 20, 12,000 joules. I'll just put in brackets there, 12 kilojoules. Okay, so we've almost got everything we need to work out how powerful these two lifts are. So remember that the power of the crane, how powerful it is, will be how much energy it transfers divided by how long it took to do it, and the same for the human being, the same maths. So let's do that now. So why not pause the video now and see if you can do this? Okay, so take a few moments just to work with the numbers, and can you work out for me what the power of the crane is and what the power of the human is lifting the same object by the same height? Okay, so how did you get on? So let's have a look. So we'll do the crane. And so the energy transferred by the crane, we worked out, same as the human of course, is 12,000 joules. So the power is the energy transferred in a time, 600. Okay, so the power of the crane will be 12,000 divided by 600. You can lose those two noughts, okay, and work it that way if you want, but you get 20 joules per second, or 20 watts. Now let's do the same for the human. Got to remember, it was the same object being lifted through the same height, but the human did it quicker. Okay, so for the human, the power is the energy transferred per unit time. So we've got to divide by how rapidly they did it. Don't divide by half a minute. Got to do it in seconds. 30, and that gives a power of 400 joules per second. Okay, so 400 watts. So if you look at the work we've done there, you'll notice that a really powerful, no it isn't, okay, a really big crane can lift an object, and so can a human. But if they're lifting the same object and the crane does it much more slowly, then the human is transferring energy quicker, so the human is more powerful. So let's have a quick look again at the equations that could come up at GCSE for power. Okay, so we know that power is energy transferred in an amount of time. So it's P is E over T. I think I spelled transferred incorrectly earlier on. There's two R's in transferred there. Okay, another way of looking at it is power is the amount of work done, energy transferred, per unit time, so divided by the time taken. So power is work divided by time. There are other power formulas, and there are ones for electricity as well, but these are the ones we'll deal with mechanical systems for the time being. So just to summarise on this, power is energy per unit time. So energy divided by time. But they could ask you for how much energy has been given out. So you rearrange this one, of course, to energy is power times time. So those are the equations that you need to kind of get your head around if you're going to do GCSE power calculations. Okay, so now let's have a bit of fun and do a little bit of an experiment. And you can actually do this one at home if you want. You don't need much apparatus. Let's try and work out the human power climbing a staircase. Okay, this one comes up in textbooks quite a bit. I have no idea how you do this with a class of 20 or 30 pupils all rushing up and down the staircase. So what I do is I give my pupils a weight to lift, and I say, okay, lift it up onto the lab benches 50 times. If the desks are a metre high, you know we've lifted it by 50 metres because we've lifted it up 50 times. Get a stopwatch and time it with a stopwatch so we know how long it took, and if we can work out the energy that it gained being lifted 50 times and divide by the time, we've got the power. And we get a couple of different values in the class. We get low powers, people who lifted it 50 times but slowly, and people who lifted it 50 times, same energy transfer, but lifted it quickly. Anyway, I'm on my own today, so we can do the staircase experiment. So let's work out the power of me climbing the staircase. So I need two things. How much energy have I gained, and how long did it take me? So the energy that's gained here, if you remember, is gravitational potential energy. And I've drawn the staircase. I mean, yeah, I'm not a very tall guy, but I haven't quite drawn it to scale here. It's like climbing the step pyramid in Egypt, but whatever, you get the idea. So the energy gained is potential energy, so gravitational potential energy, and that will be equal to mgh. Okay, and then all we need to do is also time ourselves to climb the staircase. So this took, and I'm going to leave a gap there, and we must do the time in seconds. I mean, it's obviously not going to take me minutes to climb the staircase. And then we can calculate my power for climbing, because the power will be the energy I transfer divided by how long it took. So we can work out the power of my climb. Okay, so what I'll do now is we'll go off to the staircase. We need to measure the height that I climbed through, and I need to use a stopwatch to time how long it takes me to get up to the top part of the staircase. Now, the time is a very short time, so really I should go back down and climb again, and back down and climb again, etc. So there is less error in the timing. But I haven't got all day to do this, so instead I will just do it once. But be aware that that doesn't give you the most accurate answer of the power to climb the staircase. Okay, so I'm ready to climb the stairs now. So 3, 2, 1, go. And I'm not doing it in a particular hurry. I don't particularly want to run around in a suit today, but I'm reaching the stop. 3, 2, 1, stop. Okay, so I've got a time for climbing the stairs. Okay, so back from the staircase, let's now do our calculation. So we'll put some numbers into the energy that was transferred by me into gravitational potential energy. So you need to know my mass. Well, it was 67.5 kilos when I weighed myself at home earlier today. So let's just round that up. How many people round their mass up? Maybe I should have rounded it down. Never mind. 60 kilograms, okay, G, the gravitational field strength, GCSE, 9.8 newtons per kilogram. And finally, the height that we went through. So I took like a tape measure and I dropped the tape measure down off the top of the stairs, and that has to be in meters. So we got 3.2 meters. I'm making the point there really clear, and I used the stopwatch, if you remember, to time myself, and that came out at 9.6 seconds. So pause the video there and see if you can work out what the power of my walking up the stairs was. So let's see how you got on with your calculation. So we know the power is the energy divided by the time. So the power is the energy that I transferred, mgh, so 60 times 9.8 times 3.2, okay, divided by how long it took me to do this, 9.6 seconds. So multiplying all that lot out on the top, and you get 1882 approximately joules of energy transferred from me into gravitational potential to climb the stairs, divided by 9.6, which was the time I took to do the climb, and that gives you the power of my climb, and my power came out at just about 196 joules per second transferred, or watts. Now, just before we finish, I do hope you got that answer, by the way. That number would have been bigger if I'd climbed higher, but more importantly, we would have got a higher power if I'd climbed more rapidly, if I'd actually run up the stairs. The other thing is that's the amount of energy that I transferred to gravitational potential. It's actually not how much energy I used to climb the staircase. I actually used more because I'm giving off heat and things. I'm not 100% efficient. So I do hope you enjoyed that video and you now have a really good understanding of what power is, the formula to calculate power, and the sort of things that would come up in an exam. So I'll be making another video soon, and I look forward to seeing you all then.